Okay, welcome to lesson 6.8. So right now I'm recording this video for the summer 2021 college algebra class, and we did not have enough time to cover this section during our in-person class time. So I've made the 6.8 homework optional. So therefore, watching this video is also optional, but especially for those of you moving on to other math classes after this one, it would be good to at least try it and review these concepts. So that's what I will attempt to do with you right now. What we're looking at right now is the video notebook, the physical handout that hopefully I've given you by now. Would look slightly different. I've adjusted it a little bit, but overall the content should still be the same. So if things look different, possibly I've skipped something or maybe changed the order a little bit, but hopefully you can still follow along. If for some reason you don't have the physical handout, let me just remind you where you can find these video notebooks. So I'm going to switch my screen momentarily. So you can get it in Canvas. Okay, so in our College Algebra 1315 Canvas course, click on Modules, and you would go to M1 Learning Lecture Materials. So again, Modules, we're in Module Unit 1, M1 Learning and Lecture Materials. And there is a video notebook document for each of our sections. So I've been handing you these in person and I've adjusted them and maybe shortened them or changed the font size or whatever, but these are more the original ones. So again, modules, M1 Learning Lecture Materials, scroll down and you'll see all these different PDF files. We're going to do video notebook section 6.8. So I clicked on that and it just opened in a new tab in my browser in Firefox here. I'm going to switch back to my other screen. I like to use Microsoft Edge. It just looks a little better for me to write on. So I'm going to go use that. But anyway, that's where you can get copies of the video notebooks if you ever misplace your physical one. All right, so this section, as you can see, the chapter number is different. We've been working in chapter 2, dealing with graphing and graphing lines and slope, equations of lines, etc. This is a different topic. This is in chapter 6, section 6.8. We are talking about functions, and specifically we're going to be really mostly looking at graphs of functions and talking about sort of the shape of the graphs. And so we have these 3 words we're going to use: increasing, decreasing, and constant. Those words probably mean what you think they do. Increasing means going up, decreasing means going down, constant means staying the same. Now, of course, you see these more complicated definitions below. So for increasing, a function f is said to be increasing on an open interval I if for all a and b in that interval a is less than b implies f of a is less than f of b. I personally find that definition very difficult to comprehend. I'm leaving it here for you to have. And I think I just need to show you this rather than rely on these definitions. It basically means if you have 2 x values where one x value is less than the other, that means their y coordinates will have the same relationship. Really what you're going to see is the graph will be going up from left to right. That's what increasing really means. Read the graph left to right. If it's going up from left to right, it's increasing on that section of the graph. So an interval is more like a section of the graph in this case. Decreasing is the opposite. So as you go along the x-axis, if a is less than b, then the y coordinates actually are decreasing. So one y coordinate will be actually greater than the other, going left to right. So you start with a high y coordinate, you go down to a lower y coordinate. F of a is going to be greater than f of b. What you need to know for decreasing is your graph is going to go down from left to right. Okay. Constant, that means your graph is essentially going to be staying the same. As you read from left to right, your y coordinates will be staying the same. Okay, so we're going to see that in this first graph. And so far I haven't written anything. Let me just jot down a couple of notes off to the side, summarizing what we just said. So we'll say increasing means going up from left to right. Decreasing means your graph is going down from left to right. constant, you probably just see it as flat. Let's see, the y coordinates are staying the same from left to right. So if you have this handout physically in front of you, this is a good time to maybe get 3 different colors, one for increasing, one for decreasing, and one for constant. And we can literally color on the graph and kind of highlight where each behavior is happening. So I'm going to do that on my screen here. Okay, let me adjust this little text box so you can actually read it. Zoom always does this. Maybe. All right. Sorry, this just bothers me when they cut off the words. There, good enough. Okay, so let's pick our first color for increasing. I'm going to highlight my increasing parts of the graph in yellow, and then we'll talk about how to answer this first question. So in the example, it says determine the intervals on which the function is increasing, decreasing, constant. So let's look for where is the graph increasing from left to right. As I read the graph left to right, actually what's happening first is the graph is decreasing, going down. Then it's flat, that means constant. And then right in this section here, kind of between the point 3, -2, and 5, +2, if I observe that section of the graph going left to right, the graph is increasing. It's going up from left to right. It's kind of like you're climbing up a mountain. So the way we would answer that to describe this interval, what you want to do is focus on the x coordinates. So as x goes from 3 to 5, the graph's y coordinates are increasing. The y coordinates are going up. It appears to have this kind of uphill look to it. So the interval, actually it's given to you below, the interval on which it's increasing is 3, 5. We always use parentheses because we always want to use these or describe these things with open intervals. We're never going to use the square brackets. We're never going to include those kind of in-between points. Those are called turning points. That's where the graph is sort of turning from one behavior to the next. So for example, at this point, 5, 2, is the graph increasing or decreasing at that point? When you come to the top of a mountain, are you climbing up or are you climbing down? You're kind of just stopping, right? You're in between. You just climbed up, you're about to climb down, but right now you're just standing still. So that's called a turning point. We do not include the 5 in our answer with the square bracket. We just leave it with parentheses. Okay, let's try decreasing now. Where is the graph decreasing? I'm going to use a blue color here. So I'm going to color or highlight the pieces of the graph where it's going down from left to right. It's actually starting on this sort of left-hand piece here. Now this might be tricky. I know we're literally seeing an arrow pointing up, so you might think, oh, up means decrease, or up means increasing. But if we read it from left to right, if we were to start at this up arrow and travel along the graph, really it is going down from left to right. The graph, the y coordinates are decreasing. So that's our first piece of the graph where it's decreasing. Then we have this flat piece. We'll get to that. That's constant. Then we have another piece of the graph that's decreasing. So there's actually 2 different intervals where the graph is decreasing. So we're going to name both of those. Okay, so for the first one on the left side, as we're going left to right, the graph is decreasing. This arrow implies the graph continues with this behavior forever, but kind of in this left-hand direction. So we're going to start our interval with -infinity. And then we're going to stop it at this point with the x coordinate of -1. So the graph, if we were to zoom out, if we had that ability to zoom out and look at what else is happening in this graph, it's just going to continue behaving this way forever in this direction. So our little number line, our little x-axis appears to stop at -3, but we know it goes on beyond that forever. And there would be no stopping point, no boundary point. This graph would continue to decrease as far as we could get toward -infinity. It would have that decreasing behavior. And then sort of on the flip side of that, all the way over here on the right side of the graph starts to decrease again when x is 5, and then it just keeps decreasing again because of the arrow we can assume that it continues to do this forever. So again, imagine that we're zooming out, picturing, zooming out. That's the best way I have to say it. Picturing, what would happen if we were to look at this graph? How would it continue beyond what's drawn here? It would continue to decrease. And I know it's going down, but you can kind of see the graph continues to get wider. It's not going straight down, right? It sort of has this ever so slight widening behavior. So if we were to continue the x-axis here and zoom out beyond my computer screen, beyond your paper, the graph would continue to behave in this way. So starting at 5, parentheses 5, all the way to infinity, the graph is decreasing. Okay, so we've highlighted almost all the pieces of the graph. The only piece we haven't highlighted is this flat piece right here. This is where the graph is constant. Okay, so notice that for both of these points here, the y-coordinate is -2. So the y-coordinate is staying the same. It's staying constant as the x-coordinates are increasing. So from x equals -1 all the way to x equals 3, the graph remains constant. So our interval that we would name for constant, it would be parentheses -1, 3. So that's the piece of the graph where it's flat. From x is -1 all the way to x is 3, it has that flat shape to it. Okay, so that's your introduction to these three terms: increasing, decreasing, and constant. As you can see, this is my approach of get out my colors, highlight, break it down into little pieces. We'll see some more examples momentarily. But if you can remember, reading your graph from left to right will really help you to kind of break this down a little bit. All right, I'm going to clear what I've drawn so far, and we're going to continue scrolling and possibly turn the page to look at some other examples. Okay, but the example we just did is sort of written out in this A, B, and C. I kind of put in my own words with you already why we picked the pieces that we did. So I'll just continue scrolling. Okay, and then we have another couple of examples. Let's look at example 1 here. So determine the intervals on which the function is A, increasing, B, decreasing, and C, constant. I'm going to zoom out so I can see all the little parts here because we have our fill in the blank. Okay, here we go. All right, so reading the graph left to right, it looks like the first thing that's going on here is it's increasing. Before I even answer the questions below, I'm going to do my highlighting again. So increasing. Right here, increasing, going up from left to right. Then what's happening next? Looks like constant is next. Then decreasing is next. Then it changes back to increasing again. So I've kind of just highlighted all the different pieces of the graph. Increasing, then constant, then decreasing, then increasing again. So let's fill in the blanks and see what we're being asked. So part A says, as x values increase from blank to -3, y values increase. Okay, so I think it's talking about this first piece here. As the x values, we're kind of going all the way in that negative direction here. So as we're going from -infinity on the x-axis all the way to -3, our graph is increasing. So I think -infinity is what we're going to put there. Also, now we're going to talk about the next interval that's increasing, the other yellow one. Also, as x values increase from, let's see, 2 to 4, the y values increase. So we're going up from this x coordinate of 2 to this x coordinate of 4. It's not about the 2 and the 4 exactly. It's about the shape of the graph and what's happening there. So when, in that piece between 2 and 4, the graph is going up, the y coordinates increase from 0 to 3. So the intervals that we're going to name are -infinity to -3 and 2 to 4. So those are your answers for the increasing intervals. There's 2 of them: -infinity, -3, and 2, 4, all with parentheses. Okay, part B for decreasing. As x values increase from 0 to 2, so that's this blue piece here, as the x goes from 0 to 2, what's happening to the graph? The y values decrease. You can circle that. Thus, the function is decreasing on this interval from this x coordinate of 0 to this x coordinate of 2, 0, 2. So notice as we're answering these intervals, we're answering always with x coordinates. Okay, so your x coordinates are your answers always. A very common mistake is for people to answer with the y coordinates because we're looking at those as well. But the intervals, it's really all about the x. Okay, part C for constant. As x values increase from, let's see, where's the constant piece? That's this sort of pink piece here. Looks like we're going from -3, 2 to 0, 2. Okay, so as x values increase from -3 to 0, the y values stay the same too. Thus, the function is constant on -3, 0. That's the interval. All right, and then there's a your turn that we could try. I'll go ahead and do it. Feel free to fast forward if you want to. Okay, I'm going to zoom in and let's see. I'll erase this. Yeah, I'm going to zoom in and that's going to erase what we've written already, so feel free to pause. Okay. So we're going to try the your turn graph. All righty, here we go. So increasing right here. So my answer for increasing would be, let's see, it's increasing. My x coordinate would be -2 and +2. So the graph is sloping up from left to right, and the x coordinates that would make up that interval would be parentheses -2, +2. So that's the increasing answer. For decreasing, where is the graph going down? Looks like right here. Now notice there's no arrow on the left side for this one. So it definitely has a stopping point. We're not going to use -infinity for our answer here. The graph sort of starts with this x coordinate of -5. There's a point there, no arrow. That's a definite boundary. So we'll start with the -5 and then we'll end with the -2. So that's the interval on which the graph is sloping down from left to right. So for part B, we'll answer with -5, -2. And then finally for part C, constant. That's this flat piece here. Now here we do have an arrow. So we will be going off, looks like, to +infinity. And the x coordinate where that interval starts is 2. So we'll start with parentheses 2, infinity. Okay, so that graph just had 3 intervals, one of each. All righty. Let's keep going. Okay, now we're going to talk about another feature of some of these graphs, which is maximum and minimum values. So when we've graphed lines, there are no maximum or minimum values because the lines go on forever. So this hasn't really been a concept that's come up yet. But when you have something like a parabola or all different kinds of graphs, they might have a maximum or a minimum. There might be a highest point or a lowest point. Okay, so once again, we have these kind of complicated definitions. Again, I personally have a little trouble getting a lot out of reading these and understanding, but they're there for you. I think visually, if we take a look at some examples, I think it'll become more clear, okay? So the definitions are here. Let's see. So, yep, no, I'm not even going to read them out loud. They're there. Let's look at some examples of graphs. All right, so here's a graph. It's kind of curvy. The maximum point and the minimum point, the way I would describe them is it's like the top of a mountain and the bottom of a valley. And when we have the word relative maximum or relative minimum, it means it's not an absolute max. So here, let me write that. So absolute maximum would be the highest point in the whole graph, whereas a relative maximum is the highest point in a certain interval or piece of the graph. So for example, if you climb a high mountain, you might not have climbed the highest mountain in the world, but maybe you climbed the highest mountain in your town or in the neighborhood or whatever. It's high relative, you can see all around you in the close area of where you are, but you're not in the highest mountain in the whole world. It's kind of a simple comparison, but that's sort of what we're talking about here. So this graph doesn't have an absolute maximum because there's an arrow here. It goes on forever. It also doesn't have an absolute minimum for the same reason. But if we zoom in on sort of the center of the graph where it's curving and changing behavior and changing directions up and down, that's where we can describe a relative maximum or a relative minimum. So let's start with this sort of hilltop shape right here. I've just colored on it in yellow. This point represents a relative maximum. Okay, now sometimes you'll be asked for a maximum value. The value is the y coordinate. So in this example, the relative maximum value is 4.830. Okay, so let's make a note of that. When you see the word value, like function value or maximum value, that's going to be the y coordinate. Okay, so it occurs at an x coordinate, but the value itself is the y coordinate. So occurs at the x coordinate. Okay, so you can see that next sentence. It occurs when x equals negative 0.2 or 0.728. So for example, the height of your mountain, I don't know, I don't climb mountains. So the height of your mountain is, I don't know, 2,000 feet. But it occurs 5 miles away from my home. Those are two different measurements. I'm not climbing a 5-mile high mountain. That's the horizontal distance that I traveled, but the height of the mountain, that's the highest value. So those numbers have two different meanings. One is how far away are you from the origin horizontally? That's the at one, where it occurs. Where does this maximum occur? And then the value, what is the maximum value? That's the y coordinate. Okay, and then there's a similar answer we can give for relative minimum. Okay, so I'll just circle that one. That has that sort of U shape, sort of like a valley, where the graph changes from decreasing to increasing. Okay, so the relative minimum value is this negative 6.015. So again, that's relative minimum value. And it occurs at x equals 2.061. So that's the lowest y value in this area. Where does it happen? It occurs at the x coordinate. So again, the value is the y coordinate. Where it occurs is the x coordinate. So just some little language details to get used to. All right. Okay, and then there's some more writing here about increasing and decreasing. Okay, so let's see a few more examples. Example 1, using the graph, determine any relative maxima or minima of the function. So maxima and minima are the plural of, instead of saying maximums and minimums. But in this case, I think there's still just one of each. Let's zoom out just a little bit more. Okay, I don't know if I can fit it all. Almost. All right, so let's look at the graph. We see the relative maximum value of the function is, okay, so let's circle that one. Here's this point. That's the relative maximum. So the value is the y coordinate, so that's 2.282. It occurs at x equals negative 0.236. We also see that the relative minimum value, so there's this minimum point, that little U-shaped valley shape of the graph, the relative minimum value, that's the y coordinate, negative 1.282, and that occurs at x equals negative 1.764. Okay, and next it's going to talk about increasing and decreasing. Okay, so the graph starts falling or decreasing from the left and stops decreasing at the relative maximum or minimum. Okay, so let's think about that. I'm going to draw that out to understand what this is saying. So it starts falling or decreasing, okay? And it stops decreasing at the relative, we're going to say minimum, right? If it decreases and then stops decreasing and changes back to increasing, that's a minimum, okay? Okay, then it increases to the relative maximum. And then falls again. Then the function is increasing on the interval. Okay, so where is it increasing? It's sort of this middle piece right here. I'll highlight that. Increasing. Oop. So it's increasing from, let's see, that now we're talking about the x coordinates again. We're talking about intervals. So increasing from x equals negative 1.764 until x equals negative 0.236. Okay, so let's fill that in. Okay, the first one's already filled in. 236. Okay, and then it's decreasing on these two different intervals. Okay, so the first one is this one here. Oops. Let me do a better job of highlighting that. Decreasing and decreasing. So those two intervals are what we're talking about. The first one, I'm all the way down at the bottom of the screen. Hopefully you can still see. So that first interval, we would say it goes from x is negative infinity all the way to x is this negative 1.764. So that, those x coordinates are the same here. The relative minimum or relative maximum, it's sort of where the graph is changing behavior. It's changing from decreasing to increasing or vice versa. Okay, and then the other interval where it's decreasing is from negative 2.36 all the way to forever. So as the x-axis continues towards infinity, this graph will just continue to decrease. So we're going to fill in infinity here. All right, there we go. So that's example 1, I think. So feel free to pause and make sure you got everything. I'm about to clear all that I've written so far. All right, I'm going to skip the your turn for now. Sometimes we skip it in class. Okay, so on your video notebook handout, I did not give you these pages. If you get the video notebook online, you might see these pages that have things crossed out. That just means there's certain topics provided to us by the book that we are not covering in this class. So I'm sure you won't be disappointed to see these word problems crossed out. Okay, so we're skipping ahead to the next topic, which is piecewise functions. Okay, and there's this little type of function that's crossed out called the greatest integer function. I don't think that's even on your handout at all. But if you're looking at the digital version, you'll see it crossed out. So piecewise functions. All right, so functions have different formulas for different parts of their x values. So different parts of the domain get plugged in different ways. Okay, let's see what this looks like. So for the function defined as f of x equals, then we have three different formulas, x plus 1, 5, or x squared. It's like a choose your own adventure, choose your own function. How do you know which one to use? Well, you have to check which piece does your x value belong to, which group or which part of the domain. So here's the first one, f of negative 5. So we have to ask, where does negative 5 fit in any of these intervals? It's not the last one, because negative 5 isn't greater than 3. It's not the middle one, because negative 5 isn't between negative 2 and 3. It's actually this first piece, because negative 5 is less than negative 2. That's the piece that makes sense, right? So since negative 5 is less than negative 2, we plug it into that first formula right here, x plus 1. And we've plugged into functions before. We found function values before. So we replace x with negative 5, get negative 5 plus 1 is negative 4. Okay, then the next function value that we're finding is f of 0. So which piece does 0 fit into? So 0 is not less than negative 2. 0 is also not greater than 3. 0 is between negative 2 and 3. Okay, so since negative 2 is less than or equal to 0, which is less than or equal to 3, since that's true, we use that middle formula right here, which is f of x equals 5. Now this is the easiest of all, but a lot of times people get this wrong by thinking they have to do something with the 5, like multiply by 5 or add 5 or something. It's not 5x, it's literally just 5. So it just means this is a constant part of the function, by the way. So no matter what, all these x values, the answer will just be 5 all the time. So there's nothing to do with the 0 other than just realize, oh, I guess f of 0 is equal to 5 because that's literally the formula, f of x equals 5. Okay, next one, f of 3. That one goes to the same piece because 3 is equal to 3. So it just barely fits in that interval. It doesn't belong to that last piece. 3 isn't greater than itself. 3 is equal to itself. So this is, we get to use the formula again, and f of 3 is also equal to 5. And finally, the last one we're asked to do, f of 10. We get to use this last piece of the formula, this last piece of the function, sorry, because 10 is greater than 3, we get to plug into f of x equals x squared. So f of 10 is 10 squared, which is 100. So notice how for this type of function, it's sort of like 3 in 1. It's 3 different functions put together in one. So you have to pay attention to which part of the domain your number belongs to, which interval it belongs to, and that will tell you what formula to use. Okay. So here's example 1. G of x equals, we have 3 different formulas, 3 different intervals. Let's find the answers for these 4 different function values. So g of -2, let's see, seems like they're giving them to us in order, which is slightly convenient. So it looks like we can use that first piece here. Because -2 is less than or equal to -2, we'll use that first, or excuse me, because -2 is less than or equal to -1, we get to use that first formula, x squared minus 1. Okay, so yeah, that's literally what it says right here. So g of -2 will plug into this formula, x squared minus 1. -2 squared minus 1 becomes 4 minus 1, which is 3. Okay, now the next one, g of 1. 1 belongs to this sort of middle interval because 1 is between -1 and 3. So we'll plug it into this little formula, -x. So g of x equals -x. That means g of 1 equals -1. That's it. Okay, then we get to do g of 3. Okay, I don't know if you can hear, but I'm in my home near my pet guinea pigs and they just started squeaking. So if you hear squeaking, they're just hungry. Okay. All right, let's see, g of 3. So again, we get to use that middle interval one more time. 3 is between -1 and 3 because it's actually equal. It's equal to itself. So it just barely fits into that interval. So we get to use that same formula. G of 3 is equal to -3 because we're just using this formula, g of x equals -x. And finally, for the last one, we're finding g of 4. 4 fits into this last interval because 4 is greater than 3. So we get to use the formula g of x equals 6. Therefore, g of 4 equals 6. All right, there you go. So that's example 1. All right, feel free to fast forward through this next part. I'm going to do the your turn. Okay, so let's try f of -5. We'll look at our new function up above here. Because -5 is less than -2, we do get to use that first formula. So we'll use the 2x plus 3 formula, which means we'll do 2 times -5 plus 3, which is -10 plus 3, which is -7. All right, next we'll do f of -2. Ooh, let's be careful here. Okay, -2 is not less than itself, so we're not going to use that first formula. -2 fits into this middle interval. So it's equal to itself. It's equal to -2. So it fits in this middle interval of numbers that are between -2 and 1, including -2 and including 1. So that means we get to use the formula f of x equals 1. Therefore, f of -2 equals 1. That's always a weird one. People get that one wrong all the time. Don't overthink it. It's just telling you the answer is 1. That's it. Nothing for you to calculate at all. Okay, same thing for f of 0. It's in that interval as well. It's between -2 and 1. Therefore, again, we use this formula, f of x equals 1. So f of 0 equals 1. And finally, the last one, f of 3. We get to use this last interval because 3 is greater than 1. So it fits into that x is greater than 1 piece. So we get to use the formula f of x equals x squared. So f of 3 equals 3 squared. And that's 9. So there you go. That's another piecewise function example. Okay. Possibly you're turning the page at this point. All right, and the next thing we get to do is some graphing. Okay, these are a little annoying to do. I will just say that's my personal opinion. So I'm going to fill in the tables that are given to us. And then when we do the your turn one, I'm going to use a different approach that does not involve tables, but instead involves slope and y-intercept. I just feel like that's easier. I'm just scrolling down. Okay, so yeah, it's giving us the final answer. All right. Let's see. So graphing a piecewise function. So g of x equals, we have these two different formulas, 2x and x minus 3. G of x equals 2x for x is less than -1. G of x equals x minus 3 for x is greater than or equal to -1. So it's two pieces or two parts. So it says first we graph g of x equals 2x only for inputs that are less than -1. So they just picked some numbers. Why did they pick a fraction? I don't have a good reason for you. So I wouldn't have picked that one personally. It doesn't really matter as long as you're picking numbers that are less than -1. I guess they probably picked this fraction because it's close to -1. This -3/2 is technically -1.5. Okay. What I would also do is I would actually plug in -1, even though it's not going to be included. I like to know where the graph would end. So if we plug in -1, if we do 2 times -1, that would be -2. This point, -1, -2, it's going to be an open circle on the graph. So we'll just get ready for that when we look at the graph momentarily. Let's see what's already been done. Each of these numbers has been plugged into this formula of 2x, so they've been multiplied by 2. 2 times -3 is -6. 2 times -2, we can fill in -4. 2 times -3/2 just becomes -3, and that's already been done as well. So if we look at the graph, and mine's not on the screen right now, but if you look at the graph, you should see those points plotted and more. And basically, it's sort of a line segment that's been graphed here. I'm going to clear this writing and scroll down so we can take a look at that piece. And let's see if we can zoom in. Okay, so that's this left-hand arrow here. I'll just highlight that. Okay, so I guess the pieces, the points that we would have just plotted, let's see. I don't know if you can see it, but see that tiny little open circle? That's the one I was talking about, the -1, -2. -1.5, -3 would have been here. What else? I already forget. -2, -4, etc. The way I think about this graph is I think about graphing y equals 2x. So I think of the slope as being 2. So you could really just maybe just start with 1 point and go up to over 1. The trick is we can't really start with 0, 0 because that's not in the domain. So anyway, there's different approaches you can take. I think filling in the table works just fine. It's okay. All right, let's go back and see if we can make sense of this other piece of the graph that uses a different formula and will result in sort of a different line segment with a different slope. Okay, so g of x equals x minus 3 for x is greater than or equal to -1. So this time we can plug in -1 and have an actual point on the graph that's included. -1 minus 3 would be -4. So that's this point right here on the second piece, -1, -4. Here are some other points. I might have chosen 0 as well. 0 minus 3 is -3. So the numbers that they chose are kind of arbitrary, kind of random. You can choose any numbers as long as they fit into that inequality. So -1, 0, 1, 2, 3, 4, 5, etc. Okay, so 1 minus 3 is -2. 4 is another one that works. 4 minus 3 is 1. So you could kind of highlight where those points would go. And you need to connect them. And just notice that you're forming a line. Again, I would bring us back to understanding slope here. So y equals x minus 3. Our y-intercept is 0, -3. And that is, that's right here. That is included in the domain here. So we do get to plot it. Our slope is 1. So we can go up 1 over 1. We would just need to know kind of where to stop. If you choose to do the homework for this section, I think in terms of the graphs, they're all going to be multiple choice options. So you get to sort of narrow it down based on slope if you want to, or you can use these tables. Okay, let's try the your turn. Here's what I mean by using slope. Let me attempt to show you that. Okay, so let's see. Graph the function defined as f of x equals -x plus 2 for x is less than or equal to 3, and x minus 5 for x is greater than 3. Okay, so let's start with the first piece. X is less than or equal to 3. So if I were to make a table here, I could include 3. 3 is equal to itself. Then I would want to also include numbers that are less than 3, like 2, 1, 0. So let's just start by plugging in 3. -3 plus 2 would be -1. So I could plot 3, -1. Okay, what else? Let's see. Let's plug in 2. -2 plus 2, that would be 0. So 2, 0. -1 plus 2 would be 1, so 1, 1. -0 plus 2 would just be 2, so 0, 2. And this would continue. So I hope what you're starting to see is this is a line segment. It's a line, part of a line. It has this y-intercept of 2, right? If you, again, think about y equals mx plus b. B is 2, right? There it is, 0, 2. And we do have this slope of, because of that negative sign in front of the x, we have a slope of -1. We just can't continue the line forever in both directions. We have to keep this 3 as a stopping point, but we can continue it in the less than 3 direction. So we can continue it sort of to the left. So I can extend my line segment to the left. That would be my first piece. Now for the second piece, we use a new formula for all the values of x that are greater than 3. Okay, and the formula now is going to be x minus 5. So if this line were allowed to cross the y-axis, it would have a y-intercept of -5. This one's not going to, because it's going to be off kind of on the right side of the screen. But if we were able to extend it, it would cross the y-axis at -5. It's going to have a slope of +1. So we'll just keep that in mind. If we fill in our table, let's pick numbers that are greater than 3. So how about 4, 5, and 6? We'll plug them in. 4 minus 5 is -1. 5 minus 5 is 0. 6 minus 5 is 1. Let's start by plotting those points. So 4, -1, 5, 0, 6, 1. And we could continue. So there's our line with positive slope. Now, we do need to extend it just a little bit. So you know how I can't really include 3 because 3 isn't equal to itself? I'm going to put it here, and I'm going to plug it into the formula. 3 minus 5 would be -2. This is going to be an open point or an open circle. It's not included, but that's sort of the ultimate boundary of where our graph would stop. Because if you think about it, 4 isn't the first number that's greater than 3. What about 3.5 or 3.5 or 3.2 or 3.00001, right? All those other non-whole numbers that we never think about, they are technically part of this as well. Okay, so I am going to leave that point open because x can't equal 3. I can't include it, but I can get super, super close to it. So anyway, as I already said, on the homework for the MyLab math assignment, I believe you can just sort of narrow down the choices of your graphs. And if you think about it in terms of slope, that might help you to choose the right graph. All right, so that was your turn 2 for graphing piecewise functions. And I think now we get to scroll past some crossed out stuff. There's these funky graphs that are, it's called the greatest integer function. They are interesting. I don't think they're that hard, but we don't do them and it's fine. Okay, and then we get to the practice exercises, and I'm going to leave I'm going to leave those undone for now. I think the goal here was to go through the notes that we would have done in class if we had if we had enough time. So I will end here, and please let me know if you have questions or want to talk about this more, send me an email, etc. Okay, so that's it for lesson 6.8. Thanks.